All right, let's go. Hi, this is Hacking Your Home. If you were supposed to be in a different session, you are in the wrong session. If you were not supposed to be in this session, this is a really good session, and you should be in this session. Thanks to the organizers for giving me absolutely no time to set up all of this. Hopefully we can make it work. So for the next 30 minutes, or 27 minutes and 57 seconds, I'm going to be the man who will be standing between you, all of you, and beer. So, also I would like to say that if anybody of you think that this talk has anything to do with home intrusion, circumventing alarm systems, picking locks, anything like that, I am very, very sorry, but you have been misled. But please do find me after this talk with a number of bills, and we can fix this, I promise you. So, my name is Karl Henrik Nilsson. I work for IoT, the company which nobody can pronounce. Everybody has their own way of saying it. I'm a Microsoft.NET MVP, and none of that actually matters the least. The sole reason why you should listen to me talk about hardware is because I have this graph. This graph represents the number of times my toilet is averagely flushed on a weekday. So I hope you trust when I say that I have the qualifications necessary to speak about hardware to you guys. I would like to give a warning. This is my office after I found a hobby for building hardware. It tends to degenerate. I don't know where it comes from. All right, so let's get started. Water. So how many people remember the first LAN party? Lots of people. Judging from your age, I'm going to guess that you had BNC networks. Like the old one, the cable, and if one of your friends went home, everything just died. Right? Yeah, okay. And this has made a lot of people think that the first networks or the first communication system were wired. And this is a flawed. I mean, we've had communication system with wireless long before we had actual wired communications, being maybe the telegraph, the first one. Well, I mean, the Indians would be like, and they would be sending, messages going forward, and we'd have number of systems. If you go back to like Lord of the Rings, they had these big piles of wood that they would light and ask Gondor to come for their help. Lousy ping time and respond time, of course, but still, it was there. So, I'm going to talk to you about how we can actually reverse engineer wireless transmission protocols, the things that in your home that make your simple toys, your simple things talk to each other, and why on earth you would want to do that. And I would like to start with why on earth would you want to do that? And the reason behind this is that it's very basic if you want to do home automation. Like if you want to control devices in your home, if you want to read data, do fun stuff, quantify yourself, like some previous speaker talked about, you're going to need to know how this actually works. There are a number of systems that can do this for you, but I'm going to talk how to build the systems that does this for other people. So this is not a talk about Telstick or anything. This is more like a talk about how to build the things that are Telstick. All right? It is an extremely learning experience to reverse engineer hardware. Because how many people here have ever started building an app and never finished it? Yeah, okay, you're my audience. So the thing is that if you have something that actually gets data, like, okay, I read the temperature. I read the temperature of my meat in my oven. Well, suddenly you're actually going to want to have something that can show you or give you a signal that you should run home because your roast is going to be perfect in like 5 minutes. And it gives you a reason to actually finish your app. And it gives you a reason to continue to do that because your wife is also going to like that app and like, fix it! That's actually awesome. Also, I hope there is nobody doubting that the first person. I'm going to get to that, sorry. It's also a lot of fun. I've had so much fun when I work, and I've had struggled for like 3 months fixing something, trying to figure out something, and one of my coworkers, well, have you tried this? Bloody. And you're just like, Now, you know what? I have flexible work hours. I'm going home. And you go home and you try it, and it's the best. I mean, sex has nothing on this. And you just fix it, and it's just lovely and wonderful and amazing. So, to start with, why on earth did I do this? Why did I figure out how you reverse engineer things? I'm going to go back 10 years in time. I was living in the north of Sweden. Authentic picture, don't be scared. And I was going to work. So I shoveled my way to my car in a rather, quite a few words of cursing, I would say. Quite a few words. And found it in what I remember as this state. So I grabbed what tool I could find. I'm really glad I didn't have TNT. And I hacked my way into the car. And suddenly I got it open, and it actually started, which was quite surprising. So I got into the car, and it started, and off I went towards my work, where I was working. And for some reason, all the Swedish car developers have all chosen materials for the steering wheel that very, very well conveys cold. So you're trying to, like, I don't want to hold this. And I pass a sign. I thought, going down the road, and suddenly I pass a sign, and it says, "Are you tired of a cold car?" Yes. And the next sign said, "We sell car heaters." Hey, I want to buy something from you guys. So I run in there, and it's like, "What does it cost?" And they're like, "Oh, £500. Oh, fine, awesome, I'll take it. I sat in their break room, coding, working on distance, while they installed it in my car, because I wanted it. And I went to work, and I plugged it into one of the electrical outlets outside in the parking lot that I finally realized what they were there for. And when I came home out of work after like 8 hours or something like that, my car was nice, warm, and toasted. It was also very, very good. It's not as good as figuring it out, but it was very, very good. I'm talking very fast because I have a little time, so just bear with me. If it's too fast, just raise your hand. Anyway, so I came home, and I realized that, oh yeah, this is going to cost a lot of money if I want to keep my car warm all the time in minus 40 degrees Celsius. Yes, that is an actual temperature that can occur on Earth. And my first thought was, okay, I'll use a timer. But then I realized that, okay, but sometimes I want to sleep to 9, and sometimes I go to work at 7, depending if you have meetings and stuff like that. So that's going to get tedious setting that all the time. And then I realized that, well, I could, of course, watch, and also you want to set it for different times, because if it's not so cold, you want to set it for 30 minutes, and if it's like minus 40, you want to set it for 2.5 hours. So I realized that, well, my wife also suggested that I would get up at like 6 and look at the temperature, and then start it if it needed to, and I'm a software developer, I'm not going to get up at 6 in the morning, come on. So, and that was out of the question. Also, I saw a potential to actually do a software solution. So I had recently gotten a meteorological station by my wife. A very expensive, very nice one, and I said, this one tells me the temperature, and I have things that can remotely turn it on. I want to combine those. And my wife looked at me and said, okay, will it still work? And I said, maybe. And she said, okay, if you can promise me that I will continuously still get the correct data into the house, I will not see any wires, then you can do this. If there's anybody who didn't know this, the person who invented the wireless technology were not single. All right, so let's go about how did we do this. And before you say there's an app for that, this was 10 years ago. There didn't exist an app for this back then. And why would I want to buy an app? This is so much fun. So, I don't want to hear questions about why didn't you use app X, so just thank you. Right, so first I had to pick a controller board. And back then I used a Zoacris. Today I would probably use a Raspberry Pi or something similar. And secondly, I needed a sensor. In this case, this quite expensive metrology station that my wife held very dear. It actually survived. And I also needed an activator. And I felt the choice of the Nexa one. I'm going to demonstrate with the one that is more available, I think, internationally, but the principle still holds. So I'm going to explain what's different between them in a moment. This is, of course, by no means the sole amount of things that you can actually reverse engineer. there's countless of things in your home, from fire alarms to toys to meat thermometers to these lamps that you put in the roof that change color, and it's really warm up here, and anything basically, remote control for a TV, anything actually that you want to do is quite possible to do this with. Thank you. So the disclaimer for the rest of the talk. So, how do they communicate and how can we eavesdrop on this? Most of the wireless devices in our homes use frequency shift keying. And if you know anything about radio electronics, I would suggest that you cover your ears right now because I'm going to lie to make this talk shorter than 2.5 hours. So, frequency shift keying, in its most simple term, is basically modulating a carrier wave for a fixed set of time. So if I would demonstrate this with my voice, and again, I'm still lying, but it will get you the concept. If I would demonstrate frequency shift keying with this, I would be like 0, 1, 0, 1. No, actually, that's amplitude modulation, sorry. Well, it will be 0, 1, 0, 1. Just changing the frequency of the sound would be how we convey the data. Some of them are amplitude modulated, and that would be like 0, 1, 0, 1. You get the concept. It's not very difficult. And I'm doing good time. Excellent. So to listen to these, you're going to need 3 different things. First of all, we're going to need something to listen to. In my case, it was a weather station. You're going to need something to listen with. And there are countless of radio things available, but one of the best things to start with, if you want to play around with this, is the $1 receiver chip that you can buy in most electronic stores around the globe. These ones can be purchased for like, I think you get 10 of these for $5 from most of the China stores. To figure out which one to select, like what frequency are the thing that I want to reverse engineer running at, well, it's very simple. You buy a $50,000 frequency analyzer, or you turn it over and look at the back, where it actually says. On anything that is CE marked, so anything inside Europe will probably have this marking. We're also going to need something to record with. My personal favorite are either an oscilloscope or a signal analyzer. 2 are very, very useful tools that you probably are going to try and buy, given enough time. But for this demonstration, I'm going to use one of these $1 chip, a resistor, and a audio jack. I'm also going to use a $10 sound card, because my computer doesn't have a line in, and you will require a line in. I will publish, after this talk, there will be notes for how to build all of this, but I do not include electronical diagrams anymore in my talk because it scares designers. So, once you have this $11 system, you can actually make your computer into an oscilloscope. There are a number of softwares available for this that you can actually use to create an oscilloscope with your computer, but I wouldn't recommend anyone because you can just use Audacity, which is open source, and a sound recorder that works really, really well. I'm going to demonstrate how to use it in just a minute. So don't panic. So let's try and do that. Work. Yes, thank you. So we have Audacity. I think I'm pronouncing that correctly. And I've selected line in. And I push record. And then I take the remote control for the lamp. I hold it really, really closely because all of you guys are using, okay, that doesn't work. Oh, there we go. Thank you. Come on, come on, come on. You see, I'm trying to demonstrate how to do radio communication in a room filled with radio transmitter and disturbance things called computers. So it's a bit risky, but I think we got some data. Basically, what you see how we had nothing, and then we actually got something. This would probably be quite jittery. If we would go to some place that aren't as noisy as this room, when it comes to radio signals, you would see a lot nicer curves here. But this will do just fine for demonstrational purposes. I think. That one wasn't good enough. So here we go. So 8, 9 samples, yes. Okay, so what we're looking at here is that first we have a blip of roughly 10 samples. It varies a little bit, but roughly 10 samples. And then we have a very, very long amount of silence, roughly 125 samples. Continuously looking at these packages, which we will do, we will see that we always have the same type of blips that are always equally long, but then we have a different sized of, well, no modulation. And that is because the data here is encoded in, basically we tell him, here comes data. And then if it's a 1 or a 0, it emulates that with how long time it actually doesn't transmit, which makes it even more complex to do in a room where we don't have actual access to good radio stuff. So don't do this at a conference for the first time, please. So, calculator, thank you. So what we will do with this, looking into it, oops, sorry. So what we will do with this, it takes 1 divided by 44,100, which is our sample frequency, and multiply it by 11. This gives us roughly 250 milliseconds of time. And the other one was same thing. We do 1 divided by 44,100 times 125, which gives us somewhere roughly among the lines of 2,500 milliseconds. Now, continuing to do this for each and every one of these will give us a number of values for a 1 bit, a start bit. So the start bit is 250 milliseconds followed by 2,500 milliseconds of nothing. And then we get to the first bit, which is, well, 250 milliseconds and, oops. As much this? This is like 16, something like that? This looks wrong. 17, yeah, that looks right. And that will tell us, I'm not going to do the calculations because I'm just going to tell you because it goes faster. I don't have that much time. And that gives us 125 milliseconds. No, 1,250 milliseconds, I'm sorry. All of this combined as 1 and 0 bits. And we also introduce, in the end, somewhere here, a stop bit. Come on, where are you? Here, we introduce a stop bit, which is 250 milliseconds followed by I think it's 40,000 milliseconds or something like that. So it's really, really long time between each of these. Now, that would give us, if I remember correctly, that would give us a start bit of 250 milliseconds and 2,500, no, sorry, microseconds, not milliseconds. And a 1 bit of a modulated of 250 microseconds and 1,250 microseconds. And a 0 bit that is basically just modulated 250 microseconds and no modulation with 250 microseconds. Oh yeah, also the stop is 10,000 microseconds, sorry. Using this, we could now pretend to be the remote control, because we know what happens when we push on. We can see the data, and we could write, using a transmitter, a very simple application that would transmit these things during these times. However, if we want to actually reverse engineer this, this is far from enough. Are you sleeping? Thank you. Am I boring anybody? No? So, to actually reverse engineer this, we have to figure out the bit pattern as well. And as you all know, there are 10 types of people in this world, those who understand binary and those who don't. Which isn't entirely true. There are 11 types of people in this world. Those who understand binary, those who don't, and those who make bad jokes about it. A regular bit string, when it comes to microcontrollers, are not encoded. But because that, as we've seen, a lot of the times we have quite a lot of disturbances, there are two major patterns in how you encode a binary stream the first time before you actually make them into frequencies. And that is that you add a 1 after every 0 and a 0 after every 1, or you just duplicate them and make 0, 0 and 1, 1, 1 to actually implicate, okay, this is a 0, this is a 1. Just so that you can actually know in the software on the receiver side that this is bollocks, something is wrong, I don't care about this data. So encoding 0, 1, 1, 1 would be, for this specific one that uses the first version, 0, 1, 1, 0, 1, 0, 1, 0. It's not confusing at all, right? If you download my slides, I have added extensive information of why this is and how to actually figure out which one it is. So look at that, or ask me, and I'll try and explain. That means by pushing these buttons, it looks like this if you can't see it. So by pushing these buttons, I can figure out that, okay, the first one is different from everybody else. So the first one is always different. So that is probably the start bit that tells the system that, hey, I'm coming, caress me. And the next is always the same unless you press a different button. So we can very easily say that, okay, this is the address, because if you press on or off, you'll get the same address, but the last bit will change, which in this case is the command bit, off or on. So it's a little bit of, figuring things out, but as long as you have something to look at, like this remote control, it's not that complicated. Also, there's a group button, which basically sends a totally different address, which is the address for, like, accept anything, and it sets the group bit to 1. Quite simple stuff, really, when you start to figure that down. Okay? So let's look at how it could actually look if we wanted to implement this in code. I'm going to open the worst IDE in the world. So this is Arduino. Is there any developers from Arduino here? Please come see me, I have some ideas. But I'm going to use this because it actually works and it's quite simple. All right, so the first thing we do is actually define an address. You can ignore this. This is just to actually get power to the transmitting bits of this. So the second thing we do is define the address, and then we define the microseconds to actually do this. And what I found out while doing this, that all of these are actually multipliers of each other. So it's actually quite easy to just make one of them defined, and then you can play around with the length of it depending on the quality of your crystal, the quality of your transmitter, and stuff like that. So this code is on GitHub, by the way. Then what we actually have to do is create packages. Here we go. So what we do is we actually use bit shifting. For all of you who remember C, this is nothing new, and for all of you who come from JavaScript, please see me after this, and I will find more people, and we will tell you about the wonderful thing of C. So this will actually just mask a bit string according to the way I showed you previously. We'll add the start bit first, and then it will add the address, and then it will add if it's a group command or not, and we'll add if it's a command. I haven't implemented group on this, so it's quite simple. Also, we need to delay a little bit, and for that we have a where's that? Oh. For that, we just have a delay microsecond function. So if you try to implement this on a bigger, like say you want to use a Raspberry Pi or something like that, you have to use Linux, and you have to use the drivers for the real-time operating system stuff that I don't know too much about, because you need microseconds and you need them to be exact. There are other ways to solve it as well, but that's one of the best ways I've seen. And after you've done this, you have your bit string, and you've written some really simple functions I call 1-bit or 0-bit to basically just do the 1001 thing to get him out of the control. You just shift them out. Still again, just sending 1-bit, 0-bit, 0-bit, 1-bit, and shifting them out one by one to figure out which one is supposed to be. And I've also added a little bit of code. Where did my mouse go? Oh, thank you. I also added a little bit of code for repeats because we're in a room not really designed to run these things in. So, if we were to actually put this on a microprocessor, we could issue commands from the computer. And I'm not sure this is actually going to work. It did! So what we've done now is we've taken this remote control, that also can control the lamp, and we figured out what is it actually saying and how can we mimic it. And we can mimic it quite simply by simply looking at it, figuring out the way it works. It also works with off. I'm not going to do any more demos, but just to be safe, for my next presentation, I'm going to do this. It's for the demo gods, so they'll not be angry with me. See it as a virgin sacrifice. All right, so let's go back into the presentation. So we have 1 minute and 45 seconds left until beer. This is the fastest I've ever done this presentation, so if you didn't get anything, they are videotaping it, and you could ask me and give me a beer later. So let's say you don't have a button to press. You do not have a button to press, but you have rather a weather station that you bought for some place, say IKEA. Did anybody have that cough? So this is actually quite hard, especially because one of these has a decimal in them. And the industry standard for implementing decimals on microprocessors is basically, what do I feel like today? And then they do that. So it can be anything from a number of zeros to a number of ones to basically us knowing that you're supposed to divide by 100 to a lot of other things. So the good part here is that most of these come with a humidity sensor that does not have decimals. So what you're going to do is look for like the common denominator. So I always look for no decimals, and I try to figure that out later. So in this case, you would just bit encode 48, build a similar structure that we did previously, and just log all of them until you consistently find the same data as you has on this. Sounds pretty complicated, but with pen and paper and some patience, it's actually not that hard. You can do it in an afternoon once you get warm in the clothes. But for experimentation, do try these. These are available at a very large store that used to be Swedish, but are now owned by the Dutch. I think it might be called IKEA. They should be paying me money, I feel. And of course, I will be available for questions if you have anything. Thank you so much for listening. You have been a wonderful audience. Now, I might have like time for 1 or 2 questions. So otherwise, you can reach me at the following places.
Okay, one quick question.
Hey, so my question is quick. How do you debug that Arduino code? I'm sure for me at least it's not going to work for the first time, but I think there are a lot of places where it can go wrong and the lamp with not light on.
That is very true. Is it actually? Oh, wow, that's an excellent question. Okay, so there are many, many ways of debugging an Arduino. One of the simplest ones is just getting the console commands up and running, and just, I am at this position, I have this value, and just sending it back to your computer. Like, you know, if you ever watch a JavaScript developer that doesn't know what he's doing, he is using alerts everywhere, and it's basically the same thing. You keep sending information back. But there are also debuggers, actually. For example, this is an Arduino. You do not have to use an Arduino. You can use whatever you like, but if you're using an Arduino, they're actually based on a microprocessor called AVR. And AVR is a owned by Atmel, which we all know is a huge corporation for microprocessors. So they have debuggers that work with excellent IDE called AVR Studio, so that you could hook it up and actually step code just in all modern editors that allow code debugging, see the values and everything. They cost like £50 or something like that, or £30 now even, I think. Requires some knowledge to actually get started, but there's a lot of information available to do that. Also, you have JTAG debugging, which can do the same on the AVR, but you're still going to need specific hardware to do that debugging. But there are available debugging units that can actually allow you to step code and see code and do stuff like that for a very reasonable price, around £30, something like that.
Yeah, and the last question. During your presentation, I had this question in my mind. What about if you are trying to decode some encrypted data between two devices? How do you handle that?
I'm not sure I understand.
Or how do you reverse engineer two devices that they are communicating encrypted?
Very good question. Very good question. So decryption is actually very hard, especially because you have no real reason. Sorry, you have no real way of figuring out what is actually cryptation and what is just encoding. So what I usually do, this is like advanced stuff, so bear with me. But what I do when I try to do this is that I have a signal analyzer called Saleas Logic Pro 16, which is a logic analyzer where you can just put on every pin on a microprocessor and see all the things it tells. And usually, you can read the information of the sensor using this, so you know what data is going in, and you can also figure out what data is going out to different parts of the system, like telling the display or something like that, which will not be encrypted. So you can use that to read the actual data in and see, okay, what should the value have been? And then you can try and figure out how is it actually encoding things. Because usually you can come in between the encoder and the microprocessor and see the actual data going out, and then you just have to hack the decryption, which is still a major pain in some place rare behind us. But quite possible. There are actually a number of tools. So let's say if you don't want to do it yourself, you don't want to do paper pen, GNU Radio has a number of tools that can actually do this with software-defined radio. But then you're not doing it yourself, but there are available tools to do this.
Did I mention that Karl likes beer as well? So you can buy him a beer later on. It's going to tell you more. I guess the good thing about encryption is not a lot of people use it, so you can still do it.
Yeah.
Thank you very much, Karl.
Thank you.